Okay, so we just finished a chapter dealing with interference, and that property really deals with the wave nature of light as opposed to, say, the particle nature of light or the ray optics, geometric optics treatment of light. We wish to continue that theme as we look at more properties that are generally associated with the wave nature of light, diffraction. With Huygens' principle, we saw that if light passes through a narrow slit, the waves will spread out from that point as if they were point sources. This spreading of light is what we call diffraction. So as this light is incident on these slits and spreads out from that point, we have diffraction, which from then on we can have interference. This will occur when waves pass through small openings where the width of the opening is on the order of the wavelength itself, around obstacles, or by sharp edges. In any case where the obstacle and the item in question is on the order of the wavelength of the light interfering with it, then you will see diffraction. Here's a diffraction pattern. Consists of a central maximum and secondary maxima and minima on either side of that wide central maximum. These results, where you see this kind of interference pattern from a single slit diffraction, can only be explained by the wave nature of light and not by geometric optics where you have rays projecting through the slit. Here's the result for object edge diffraction. You have a central maximum, but you only see half of the whole interference pattern as it progresses upward from that point. So the diffraction pattern is vertical from this so-called central maximum that's at the bottom. It was once stated by Simeon Poisson that the wave nature would have to show a interference pattern on a circular object with a central maximum on the other side, and at the time he was stating, well, we don't see that, so maybe this wave nature is not the way that light behaves. But soon after he expressed that opinion, it was found that if you took an opaque object, circular object like a coin, that it would exhibit an interference pattern that actually did have a central maximum on the other side. So this actually turned out to be proof that the wave nature, wave theory of light was confirmed, because geometric optics would not predict that that central maximum would occur. So diffraction refers to the spreading of waves as they pass through a slit. A diffraction pattern is actually a misnomer that is deeply entrenched, because actually the pattern that we see is an interference pattern. It's the interference of one part of the light with another part of the light. And so just like we had interference in the last chapter, this is interference as well. And the pattern we see is interference. But when we deal with just one slit, we call it a diffraction pattern. Here is single slit diffraction. The light from one portion of the slit will interfere with the light from another portion of the slit. And we think of each point on the slit as being a source of light. We can see that as this goes off at an angle, there will be some point where half of the rays of the slit will interfere with half of the rays of the other slit. And if the path difference between these rays are integral number of wavelengths, then we will see interference. In this case, if the path difference between one half of the slit and the other half of the slit is this right here, which is going to be the A divided by 2 sine theta, that will be that distance right there. If that is an integral number of half wavelengths, then we will see a minimum at that point. So the waves are in phase, they are coherent, and they are monochromatic. Half of a wavelength difference will correspond to a minima. So A divided by 2 sine theta will equal 1/2 m lambda, where m is an integer number, plus or minus 1, plus or minus 2, and so forth. Not 0, because we have a central maximum, but these are the points on either side of that central maximum which correspond to minima on either side. So the first one, plus or minus 1, and so forth and so on. This is from a single slit interference. Half of the slit interfering with the other half. So we will have that a sine theta to that point will be equal to an integer m times lambda, where m is plus or minus 1, plus or minus 2, and so forth. The intensity, in a similar type of treatment as we had for interference in the last chapter, our intensity will be equal to a maximum intensity sine pi a sine theta over lambda over pi a sine theta lambda, that quantity squared. If we combine this with double slit diffraction, then we'll have the intensities superimposed on each other. Here we see the intensity pattern for the single slit, broad central maximum, and then maxima on either side, separated by points of minima. The single slit diffraction pattern will act as an envelope for the double slit interference pattern. And hence our intensity will be equal to the intensity of the double slit pattern, which was a cosine squared term, pi d sine theta over lambda, d being the separation distance between the slits. And then we have our single slit term, diffraction envelope, relate to the sine squared of pi a sine theta over lambda, a being the width of the single slit. So as we superimpose these, we have the envelope of the single slit pattern with the interference pattern of the double slits inside, and we can see a wide maximum with all the maxima and minima of the double slit pattern superimposed on top of that. So we have the two slit pattern contained within the one slit pattern. Our interference maximum will coincide with the first diffraction minima when d sine theta over a sine theta is equal to m lambda over lambda. This will be the first minima for the diffraction pattern. Hence the number in front of the lambda on the denominator here will be 1. And we'll have m lambda over lambda. In other words, when d over a is equal to a number, integer, m, that will correspond to the mth maxima of the double slit pattern that intersects with the first minima of the single slit diffraction. If we have a diffraction grating, as might be observed here, we have a good subject to demonstrate. If we look at the grating in Darth Vader's helmet, we can see that we have a nice spacing of the grating here, which will help us to get a really good interference pattern. This diffraction grating consists of many equally spaced parallel slits. A typical grating contains several thousand lines per centimeter. The intensity of the pattern is the result of the combined effects of interference and diffraction, and it'll be superimposed with each spacing and each slit, hence giving us a very good consistent pattern of maximum separated by broad minima. Looks something like this, so that at every particular spacing of lambda over d, we'll get a nice interference peak separated by our broad minima. And hence we could use this result to measure the distance between those peaks and hence discern what the wavelength of the light is, if we knew what the grating spacing was. Here's a diffraction grating. A transmission grating can be made of cutting parallel grooves in glass. The transparent spaces between the grooves will act as separate slits. We can also do that with a reflection grating. It has parallel grooves cut in to the surface of a reflected metal, and then successive reflections will interfere. If you change the angle, that will also change the type of interference that you will get. So here's a transmission grating here on the left, and a reflection grating on the right, which is just the inner side of a CD disc. CD disc has regular grooves at equal spacing, so it's basically acting as a diffraction grating. And if you change the angle of that grating, you can change the color of the interference that you're going to see. Here's our maxima. We're going to have a superimposed maxima from all these interferences from the different slits. Our condition for these maxima is that d sine theta will be integral number of wavelengths in order to get constructive interference at all these points. Here's an application for this. Diffraction grating can be used in a 3-beam method to keep a beam on a CD, or DVD for that matter, on track. The first beam, the central maximum, is used to read the data on your CD, and the maxima on either side can be used for tracking. So if the beam goes off track and hits that maxima on either side, then it can be readjusted and put back on track. So it's used for steering your laser to maintain its position. We could also have diffraction of X-rays off a 3-dimensional solid in the form of a crystal. The crystal has a nice layered structure of atoms within the solid, and if it's a good crystal, then these layers will be consistent all the way through. The spacing of those layers between atoms is on the order of the wavelength associated with X-rays. So we could use X-rays to create an interference pattern that will help us discern what these spacings are between these atoms. Max von Laue suggested that this regular array of atoms in a crystal could act as a 3-dimensional diffraction grating, giving us information about the solid. This leads to Bragg's law for X-ray diffraction. If you had one reflection going off one plane of atoms and reflecting off, and then you have another ray coming in reflecting off another plane, there's going to be a path difference between the two when they interfere, and that path difference is going to be, well, we're going to have a d sine theta here, where d is the spacing between the planes, and then we're going to have another d sine theta here. So the total path difference between these two rays interfering is going to be 2d sine theta. So we'll have 2d sine theta is the integral number of wavelengths if we have constructive interference and actually see a interference dot corresponding to these planes. Hence, you could go back knowing the wavelength and knowing the angle and doing some geometry. You could calculate the spacing between these atoms, hence get some information about the crystal structure. So Bragg's law can be used to calculate the spacing between atomic planes. Here's how it might look. Parallel monochromatic X-rays are incident on a crystal. It's actually X-rays and in phase, so they're monochromatic and coherent. And as they hit the crystal, you get a 2-dimensional interference pattern on a 3-dimensional crystal. Hence, it's going to take some analytical study to determine what what those reflections correspond to what planes within the three-dimensional crystal. But based on the intensities and the location, you can figure those things out and figure out the structure of the crystal, and hence figure out the structure of that material. This array of spots that you see for the interference pattern is called a Laue pattern, coincidentally named after Laue. Here's a Laue pattern for a barrel, and we can see it's actually quite beautiful. The different intensities, stronger intensities will correspond to well-defined layers of atoms, and the weaker intensities for maybe different angles of atoms. Again, all giving you the structure of this crystal. Here's a Laue pattern for Rubisco. Again, same sort of thing. Very beautiful, but the location of these interference maxima will help you locate where the atoms are and reconstruct this crystal. You have to have good crystals to do this. So you can't just take any kind of substance and put it out there and expect to see a good X-ray pattern. You want to grow a nice crystal, which is a whole new science in itself, crystal growth. That's something that people were doing at NASA. They're doing protein crystal growth, where they could take proteins, grow them in crystals in space under the absence of gravity, and then you could use X-rays or some other means to figure out the structure of that substance. One way to identify different viruses. If you grow crystals of those proteins, you could find the structure and then find ways to combat it. Here's another beautiful structure, but it's simply a pattern drawn on my spirograph. So that concludes the first lecture in Chapter 38, dealing with wave phenomena, diffraction in particular. We will proceed on to more properties of waves in the next